All right. Next, we're going to talk about edge-triggered interrupts. And edge-triggered interrupts is one of those latency deals where we touch a button, we want something to happen. And so I'm interested in looking at the time between when I touch and when it happens. This is a table from the book, and it helps us sort all the hundreds of possible interrupts. In this column is the vector address. The one we're going to do today has its vector down here at B8, and it's going to be an edge-triggered interrupt on port F. And you can see from the fact that there is a single vector for all of the pins on port F that this is an example of a polled interrupt. In other words, if I have multiple pins on port F, all causing an interrupt, I'm going to have one interrupt service routine which has to handle all of them. Okay? Whereas I will also have a timer A interrupt and 0A, and that will be a separate vector. You see, that will have a vector here at 8C, and therefore, if I have a timer A interrupt, I know exactly why I had it. And I don't have to think about it. Was it a SysTick? Was it a port F? Was it a port A? I'll know it's a timer 0A. The next column that's interesting is the number. You're actually going to see this number in the processor. So if you're in an interrupt service routine, timer 0A interrupt service routine, we will see a 35 in the interrupt in one of the interrupt registers so that you know where it is. We will see that interrupt number 13 happens to be IRQ 19, and so we'll see that we were going to set bit 30, we're going to set bit 19 in the enable register for enabling, and set that bit in the disable for disabling. There are lots and lots of interrupts. For every interrupt, there is a priority register, or there's a 3-bit priority register. And so port F, you can see, is in priority 7 register, bits 23 through 21. The timer 0A is in the timer priority 4 register, bits 31 through 39. And again, 0 is the highest priority, 7 is the low priority. Any questions on this table? You're going to need to access this table when you want to switch from port F to port E. You're going to have to see this table so you know where to find its priorities. Question?
What does the number in the IRQ mean?
Okay. Obviously, it means 16 minus the other one. Okay. This column and that column are off by 16. Okay. This is the number that goes into the This is the number that goes into the register, the interrupt priority, interrupt number in the processor. There's in the processor, there's a register which will tell you what interrupt service routine is running. Okay, that's the number that goes in there. This is a bit number which will exist in the register. So there will be an enable register. Actually, there's a whole bunch of them. And I'm going to set bit 30 to enable this guy, and I'm going to set bit 19 to enable that guy. That's what those are for.
What's that register called?
I'll get to it. He said, what was the name of the register? And I'm going to say, I don't remember. It's got the word EN in it. We'll see it. So I don't have that one memorized. In general, what we got to do is this is a edge-triggered interrupt. A ritual is ritual. We got to turn on its clock. We got to have any data structures. As we saw, there were 4 steps to create an interrupt. What are they? 4 things. They're listed here, by the way. Look at them. Okay. What are the 4 things that have to be true for an interrupt to be requested? I got to arm it. Okay. That's a bit in the GPIO register. We'll see it. We have to activate it. That's the thing in the EN register. That's the name of the register you just asked me the name of that I don't remember. It'll be EN0 something. We have to enable it, setting the I bit, and the last thing that has to happen is the busy to done state transition for requesting to setting the trigger flag. Okay? which is going to be done on an edge, by the way, an edge of that input. All right, so here's the details of the edge-triggered interrupt. So what I'm going to have is PF4 is tied to a negative logic open collector. Okay, PF4 is tied to a switch. That's what you got on your board. We're going to enable the internal pull-up. So this input is a high if the switch is not pressed. It's a 0 if the switch is pressed. So we turned on its clock. That's port F. It's an input, so we cleared the direction register. We want to enable it. And now we've got two registers in the GPIO, which will specify whether or not it's level triggered or edge triggered. In this case, we want edge triggered, so an edge change on PF4 is going to set the flag. And then down here, we're going to specify whether it's the rising edge or the falling edge, or in this case, both edges. So what I want to do is run a task, a user task right here, if the switch is touched, and I will run a user task if it's released. And what is the syntax of this? That's a parameter. What type of parameter is that? That's a function pointer. So this is an example of a hook. So that one function, one module can call a function in another module by passing a function pointer to it. So I have two function pointers that user will pass in to decide what to do when I touch and I release. We'll get to the ARM in a minute. Initializing, let's look at ARM. Okay, I also turned on the timer, but I haven't all I did was turn on the timer for timer 0A. I haven't actually armed it yet. This is a reminder, if interrupts have happened in previous classes, it will finish the instruction with the following two exceptions. Which instructions can be interrupted? Yeah, the store multiple and the load multiple. The push and the pop instructions take so long that they will actually be interrupted. So virtually every instruction will have to be finished in order for the interrupt to be serviced. It will push 8 registers on the stack, assuming you don't have floating point on. The vector address that we saw in the previous slide is loaded in. The interrupt register is set with the interrupt number, and then the link register gets this FFFFFF9. Okay? And that tells you two things. That tells you that you're using the main stack pointer, and that you have gone from a foreground thread into a background thread. If you ever see an F1, that means one interrupt actually interrupt another interrupt. Okay, so F1 would say high priority interrupt is interrupt a low priority. And this whole thing is helpful for what we saw previously, is the fact that the BXLR instruction does what? What does this instruction do? Return from what? It either is return from subroutine or a return from interrupt. And so if the link register has FFFFFF9 in it, it's a return from interrupt, and it will pull all those registers off the stack. And if it's got some address, regular address, it'll just put that in the program counter, and that's a return from subroutine. Okay. If you see an E in there, that means your lab partner's turned on the floating point, by the way. Okay, so if you see an E in that 7th digit right here, E9 means that was a floating point, and that means there's a whole bunch of stuff up on the stack. All right. So again, it will push. There are the things on the stack, just like 319K. When things go on the stack, they go in register order, and it will push basically half of the registers on the stack. If the interrupt service routine wants to use R4, R5, R6, it'll push them just like any old function. Okay. All right. Yeah, sure. Question. Yeah, go.
You talked about function pointers where you mentioned that it is used to say call a function from one module, say, to another module. But normally what we do is we include the H file in that case, and we could directly call that function.
What Mahesh was talking about is if I have two modules, like if you look at the solution here to this edge-triggered example, there is an edge interrupt.c and a switch.c. Normally, if I wanted the switch function to call a function in the other routine, I would include its H file and call one of its public functions. I'm not going to do that. You can see that if we go over to project here, you can see that the switch routine does not have access to the global functions of the other one, but rather at runtime, I am going to take a function. I don't have a circle anymore. You see this function here called fall, which exists in the main program, in the main edge interrupt.c file, and I'm going to pass a pointer to it to the other routine. So this is a dynamic linking. The linking between the two programs is done at runtime and not at compile time. This allows the user program to pass in. This is a very common thing in operating systems. So I'm not including the H file. I'm passing in the function pointer at runtime.
So edge interrupt has access to the switch.
No, Edge has access to the switch. Yes. Edge has access to the switch, but switch doesn't have access to the edge. But switch is going to call an edge function because at runtime I passed it in. So if you look at the call graph, it's bidirectional, but the link from the switch into edge occurred at runtime and not at compile time. Yeah, it's a typical of operating systems. It makes it more flexible. Yeah. Lets the user decide when stuff happens. Yeah, it's all right. You can see what it's going to do is it's just going to increment this counter and toggle a bit. Okay, that's what it's going to do. All right. See, where was I? All right. I think this was, yeah. All right. The interrupt service team either, in this case, turns out we're not going to acknowledge these interrupts. We're going to disarm, and we'll see what happens. And we're going to communicate through the globals. In this case, we communicated via calling a function, which incremented some counters. But in general, we can use FIFO queues and semaphore flags and et cetera to communicate. All right, let's describe the problem here before I show the solution. All right, here's my problem. PF4 is not touched. What level is it? If it's sitting there not being pushed, what level is it?
1.
It's a 1, high. And when I touch it, what happens? It doesn't go low. It does something bad. It bounces down its way down because of the because of Newton's second law here. Okay. Right? Because of the fact that it's got because of the differential equation, it's got m dx dt minus kx, but k dx dt kd. That's the friction plus friction minus kx, right? Because of this second order differential equation and the fact that there's very little damping, this is a undamped sinusoid, and it's going to represent itself by touch, no touch, touch, no touch, touch, no touch. And it depends on how fat your fingers are and how much money you spent on the switch, and it never looks this pretty, but it's on the order of a millisecond. Okay? And if I'm counting the number of pushes, I want 1 bomb drop, not 2, okay? Or 3 or 4 or 5 or 6 or 12, okay? And so this bounce is way slower than the processor. And so if I didn't do anything, I'd get multiple interrupts. Okay? Similarly happens is when I release it. Okay? And so here's how I'm going to solve the problem. I want to run my touch routine right here. Okay? And I want to run my release routine right there. Right? The routine that gets run when I touch is going to have virtually zero latency, a couple of microseconds of latency, because it's a real-time system. And when I release it, I want to run the user code immediately on the release. Okay? So here's what's going to happen: is in the ISR for the edge. Now, do you remember how I configured it? Which edge caused the interrupt? In the previous slide, when I initialized this thing, which edge did I choose? The rising or the falling? I choose both. Okay? I chose both. And so this edge is indeed going to cause an interrupt, because it's one of the bothnesses. Okay? And what I'm going to do is I'm going to disarm PF4. So I'm not getting an interrupt on the other edges. I won't get any more timer interrupts. But now the question is, which is it? Was it a touch or a release? Okay? So I'm going to need a global variable, okay, which I'll initialize to, I'll initialize it to, let's see, what did I call it? I called it last. All right. That's gone now. Yeah. Okay. I'm going to disarm, and then I'm going to look at a last routine. And so if the last value that I saw was a 1, what does that mean? That means this is a touch. So I'm going to call the touch routine. Right? If the last value that I saw was a 0, this is the release operation. And now what I'm going to do is I'm going to arm timer 0A to interrupt me 10 milliseconds later. Okay? So now if you look at the steps here, how long does it take to run this interrupt service routine? Approximately. Right? Approximately how long is it going to take me to disarm? A second, a year, a minute, a millisecond, a microsecond, or a nanosecond? About a microsecond. So how long is it going to take me to decide whether a global variable is high or low? Less than a microsecond. Now, I have the user task. Okay, and that may take a long time. We saw that the user task toggled a bit and incremented a variable, right? We saw that. The user task toggled a bit that said it happened, a heartbeat, and incremented a variable. So how long does that take? How long does it take to toggle an output and interrupt a variable? Yeah, so we got a microsecond here, we got less than a microsecond there, and we got, 2 microseconds here. And then it turns out it's going to take about, a microsecond to arm timer 0. So how long did I spend in this interrupt service routine? Okay. Add it up. 1, 2, 3, 4, 5 microseconds. Okay? That's how long I was there. And that happens every time I touch the switch. It also happens every time I release the switch, but we'll get there in a moment. Okay? So now what I'm going to do is I'm going to get a timer interrupt at some fixed time after. Okay? I'm going to get a second interrupt. How long do I wait? Well, however long the bounce takes. Right? However long, but not so long that you see there's a little sweet spot. If I wait too long, the guy's released the button. Okay? And so what I'm going to do in that interrupt is disarm the timer, set last equal to PF4. Okay, because that's the stable point. That's the time when the pin is stable, and then I will rearm the PF4, the GPIO. Okay, how long does that take? Again, microsecond or 2. right? 2 microseconds in here, okay? And then when's the next interrupt? When I released it. Okay? I'm going to get an interrupt right there. But last is now going to be equal to 0. You got it? Last is going to be equal to 0, and I'm going to go this way through my flow chart. Okay? And then what happens? It's going to disarm the edge triggered and rearm the timer. So I'm going to get a 4th interrupt. I'm going to get a 4th timer 0 interrupt. I mean a 2nd timer 0 interrupt. Okay? So I touched and released the switch. I used all of 5 plus 5 plus 2 plus 2. I used all of 14 microseconds every time I touched and released the switch. So, but you think about it, how often can you touch the switch? How many times per second are you touching the switch? You know, hundreds of milliseconds. And so I've used a very small fraction of the available CPU time to service this switch. But what's my latency here? How long after I touch the switch did I execute the task that said touch? Yeah, microseconds. Assuming there's no higher priority interrupt, assuming the lab partner didn't disable interrupts, this is a very low latency response. And completely debouncing. Yeah, question.
Where do you call it user tasks?
I call him, he said, what's the name of a user task? I go, let's call them user tasks.
Like, where did you call them?
Oh, yeah, sure, sure. No. So he says, show me the details, okay? So let's show you the details, okay? All right, let's show you the actual code. Okay? So we'll start at the beginning, okay? Here I'm using these 3 pins here for heartbeats, right? These are the heartbeats, so I'm going to turn on the clock, and I'll turn the clock on again, but turn on the clock, and then enable those 3 pins for, okay? And so as I alluded to, the user codes are toggle a bit and increment a counter. Okay, so on the rising edge, I'll increment PF3, and on the falling edge, I will increment PF2, and I'll increment these counters. Okay, and then in the foreground, I'm going to toggle another bit. Okay, so he said, let's follow the sequence of operations. What's the first thing that happens? I'm going to touch the switch. So what's the first thing that's going to happen? Let's go in here. Switch. Okay, come on. All right. This is the code that we just showed you. I have enabled it. I've set my two functions, my 2 user functions. I didn't show you ARM. Let's go ahead and show you ARM. What's the word static mean in this context?
Maybe to this file.
Yeah, this is a private function. Okay, functions always exist in ROM, but this is a function that is not callable by anybody other than routines in this file. It's a helper function. And to arm the device, I am going to set the mask bit in the port F for PF4 to interrupt. Okay? And then this is where the 30 came from. That's the interrupt number. This is a weird register, and it's called the enable register. That's the register you were asking me earlier. And this is one of those weird ones. Okay? It is a write 1 to set, and this is completely friendly. This does not disable the other interrupts. It looks unfriendly, right? There's 32 bits there. I'm writing 0 to those other bits. The writing a 0 to this register has no effect. And so this is not an OR equals register. This is a write a bit to it. So same thing up here. This is enabling the timer interrupt. and there's the priority. Okay, so I've armed the edge triggered on both, and so the first thing that's going to happen is I'm going to get a port F interrupt service routine on the first value. And this is the implementation of the flow chart that was illustrated in the previous picture. So I'm going to disarm, which means no more interrupts from the GPIO. I'm going to look at the variable last, which is either going to be a 16 or a 0. If it was a 16, that means we just had a touch event, and there's a semaphore, sets a semaphore, and then the question you asked is, how do I call a hook? Okay, if I have a function variable, how do I call it? I dereference it and then call it like a function. So that is the execution of the user task associated with touching. And there's the release, and as you remember, at the end of every rise or falling edge, I'm going to arm the timer, right? I'm going to arm the timer up here. I'm using, in previous timers, you use periodic mode that generated a periodic interrupt. This is one-shot mode. Interrupt once and don't do any more. There's the time in which I'm going to interrupt. This is a 16 megahertz clock, so that's 10 millisecond time. No prescale. One of the things that Valvano always does in his rituals is clear the trigger flag, just so that an edge, so that the busy to done state transition, the trigger edge, has to occur after the arm and not before the arm. So in both cases, I will clear the trigger flag during the arming operation. There's the enabling it in, it's the TATO, timer A timeout flag that I'm arming down there. There's the priority. Here it's enabled in a nested vectored interrupt controller, and boy, oh no, that's the, and then I'm enabling the timer. All right, so then what happens, right? 10 milliseconds later, I'm down here in the interrupt service routine. And again, you can see that these are very short, okay? This is another Valvano rule about interrupt service routines, okay? We sort of estimated it, remember? Not much time. We want our interrupt service routines to be very short. Why? It is really important why. It affects the latency of the other interrupts. Okay? So no output to the LCD screen, no waiting for a switch to be pressed, no waiting 10 milliseconds to interrupt service routine. Interrupt service routines have to be short and bounded. And that's how we're going to guarantee that all of our devices have low latency. Next, let me show you how to debug it on the board. Okay, so in order to see what happens, we see I've connected it up, my board, to a logic analyzer. So we're going to be able to see PF1, 2, and 3 as it executes. All right. Let's put a couple of breakpoints and sort of walk through the process. Again, we saw last time that what will happen first is we're going to get an interrupt in the edge-triggered interrupt sequence. So let's put a breakpoint here, and then we're going to put a breakpoint in the timer interrupt. So we can see which of these two interrupts occurs first. All right, so let's build, download, debug. All right. Here in the watch window, we can see the two global variables, fall count and rise count. And so let's go ahead and start this. And so it's in the foreground process waiting for an interrupt to occur. Okay, so let's push the button over here and see what happens. All right, so we got a touch interrupt in this interrupt service routine. Okay, and that is going to, if I run it again, you will see that will call this routine here, and this routine will increment the fall count. And then arm the timer to cause an interrupt 10 milliseconds later. So let's push the go button here. Go. All right. And so our next interrupt occurred 10 milliseconds later, and it's here in the timer interrupt. You see I've got my finger on the button still because that's simulating how this will happen. All right. And the purpose now is to capture into this variable, capture the current value of PF4, which will be a 0 because I got my finger on the button. So I touch it again, I go again. All right. And now my finger is pushed, and now I'm going to get another interrupt when I let go of the button. So here I am, let go of the button, and you can see I got the third interrupt in the interrupt service routine. This time, if we watch it execute, it's going to call the release function, which will increment this variable right here to 1. And then if I go one more time, you see that I ended up in the timer interrupt service routine for a fourth interrupt. All right, so that's this. So let's remove the two interrupts here. Let's remove the two interrupts and let it go. So this time I want to show you what it looks like in the logic analyzer. All right. Let's move it down here so we can see both the logic analyzer and the watch window. All right, logic analyzer. All right. Let's first zoom way out. You see I've zoomed out to 1 second, and now I'm running. And you can see PF4 is touched, and that immediately makes PF2 toggle. All right? And then when I release, that makes PF3 toggle. And the main program's toggling PF1. So touch causes and release causes. Now, in order to see the latency, let's go ahead and zoom way in. So rather than looking every second, let's look at every microsecond. Okay? And now I'm going to take a single edge right here, a single run, and then when I touch it, I see that the touching event caused this button to fall, and I got a software execution at about 3.5 microseconds later. So our latency here is this 3.5 microseconds. All right. So in summary, what we have are two interrupts, one which occurs on the touch and release, and the second one which occurs 10 milliseconds later, which allows me to capture the correct value of the input. All right. You try it. Remind yourself that whenever you have a non-atomic sequence to a shared global and there is at least one write, look for the problem. There are lots of different scenarios, 3 of which are read, modify, write, write, read, and we saw a read is critical, assuming that this guy here can interrupt there. All right. So in this lecture, the summary is that look at the link register. It'll tell you where you are. We saw that we were very interested in latency, and we used that. We used 2 interrupts to implement a debouncing. So when you click the button on the increased time, that you got 1 increment and not 5 increments. So your role here in lab 3 is to develop your skills associated with interrupts in a much more mature way. Questions about lab 3? What we're going to do next is we're going to show you this circuit here. And so if you want to go ahead and start your lab 3. if this is the speaker there, and this is going to be a PN 2222, and we're going to generate a square wave right here, and that's going to make the speaker buzz. So we're going to talk about next time how it is we use a BJT, to implement and interface a speaker so that we have sound. Questions?